So a little bit of linear algebra, just to kind of gear us up to understand the whole concept of change of variables, which is really important when it comes to working in different bases. All right. So it's kind of weird because the term I just said, bases, BASES, looks an awful lot like bases, right? And it actually is pronounced that way also. It's just I try to like really lean into it just to emphasize that it's the plural of basis, right? So something is a basis for a system. Like if the whole system is based on a particular number, like the XY coordinate system is based on the number 1, then one serves as the basis of the XY coordinate system. But you could also look at it and say, well, what if I want to distinguish between the 1 as the basis for the X values and another 1 for the basis of the Y values? Then 1 would be a set of bases or bases of the XY coordinate system. So it's a little wordplay that kind of messes with you a little bit, but that's the whole thing. It's kind of like the whole dice thing. You know, I always explain that because I don't want people to look at a worksheet and think that I'm threatening them or something. Right. So to learn the definition of a determinant, that's the objective. The example is a very simple example. It doesn't seem to have any place in what we're doing, but it's going to connect. It's all going to come together. All right. A determinant gives the area of the parallelogram created by 2 adjacent vectors. It also gives you the volume of the parallelepiped created by 3 adjacent vectors that serve as the corners of that parallelepiped. All right. So that would be the 3 by 3 case. All right. Those areas could actually serve as a basis for any geometric figure if you want. All right. So it's a good place to start. If we want the area, we could do one of 2 things. We can actually physically find the parallelogram. I'll show you real quick. You know, you went up over 1 up 2 from 0 to get to the tip of U. So go over, I think I said over 1 up 2. I meant to say over 2 up 1. And you can create the opposite side of U. Same thing with V. That's up 2, up 3 over to the right 1. Now you have your parallelogram. All right. So if I want the area of that parallelogram, a way of handling that would be to subtract off the areas that I don't want. So I don't want this rectangle or square. I don't want that one. You know, 1 by 1 gives you an area of 1. 1 by 1 gives you an area of 1. These look like 2 sets of congruent triangles, each one having areas of half the base times the height. So half of, we'll call the base 2 here, and the height 1. All right. So that looks like a 1, and it actually makes sense geometrically because if I take this little piece off and put it over here, that would make 1 full box. That feels right. All right. So another half the base times the height over here. All right. So half the base of 1, the height of 3. We're looking at 3 halves. All right. So this guy over here is 3 halves. This one has the same dimension, so also 3 halves. These 2 have the same dimension, so each of those are 1s. So the area of the things that we don't want 1 plus 1 plus 1 plus 1 plus 3 halves plus 3 halves. So 3, 4, 5, 6, 7. We don't want 7 square units of area out of the total area of the rectangle, dimensions 3 by 4. So what would be left over would be 5 square units. So 12 minus that 7 would give you a result of 5. Right, so clearly we don't want to do it that way, but that's a way that works. You could also do base times height if you could figure out the length of u and the distance between opposite vertices of the parallelogram, or you could find the determinant of the 2 by 2 square matrix. Right, so we'll call this matrix A. So we'll call this matrix A. All right, what we'd be looking at is A that would be a 2 by 2 square matrix. All right, so A with dimensions 2 by 2. All right, and so those 2 dimensions would be made up specifically of the vectors u and v. All right, so what we would do is we would actually make this matrix have components in column form of u and v. You can go column or row form. It doesn't make a difference in normal cases, but for what we're going to do in terms of the transformations, it's going to make it a whole lot easier to put it in column form. All right. So what we would say is this matrix would consist of u and v as its columns, specifically 2, 1, 1, 3. All right. And so what we're looking for is the determinant of matrix A, which is written as an absolute value of the entries in the matrix. Now, we learned previously that when you're dealing with a 2 by 2, you have a couple of ways of handling this. One way would be the diagonal down minus diagonal up approach. Actually, you have a bunch of different ways. The other way would be to use cofactor expansion, which is how we came across the idea of the cross product. But then we could also, we could also just use a calculator, right? So if you wanted to use a calculator, you'd have to go to the Desmos calculator, Desmos matrix calculator. Let me go to my bookmarks under this one. No. Running for weight loss, no. Foam rolling, very helpful, but no. Desmos, sphere, no. Okay, well, I guess I'll just have to type it in. Filipino superstitions. My wife apparently got into this. Justin Timberlake apparently is very big on her. Okay, well, that sucks. So Desmos.com. Matrix. I mean, you could actually go to Desmos.com and just click around. All right, so you put in your new matrix. It automatically defaults into matrix A. We put the matrix having components that are column vectors, which is pretty standard actually, but we have to type it in row by row. Okay, so 2, 1, 1, 3, and then determinant of matrix A gives you a result of 5, which is what we figured out next. Okay. Now we could also use the concept of cofactor expansion. Right, so the example on the bottom or towards the bottom, both of them actually, is just kind of a review of those things. All right. So if we want to compute the determinant of a 2x2 square matrix using cofactor expansion, I mean, you could use the model. You're working in the jth row. I'm sorry, jth column. It's I rows, j columns, and then following the model that you see. So if I do it with a 2x2, it kind of seems like you're doing more work than is necessary, but it still works, right? So if we're starting off in the first row, we're looking at -1. Oh, well, let me write the proper notation. Determinant, or a proper notation, of matrix A. Bracket or bracket inside parentheses, it's the same thing. All right, both acceptable notation. So -1 raised to the 1 plus 1, a sub 1, 1, determinant of matrix A sub 1, 1, and then plus, it's j going from 1 to n. So the j value here, here's j equals 1. Oh, lowercase j, let's not get too cute. J equals 2. This is I equals 1. And this is I equals 2. All right. So just a little bit of a refresher. For the next entry, -1 to the 1 plus 2, a sub 1, 2, determinant of a sub 1, 2. All right, so put that in parentheses or brackets, I should say. All right, so -1 to the second power is going to be a +1. The entry a sub 1, 1 is 2. And then the determinant of whatever is left over when you eliminate the row and column that contains the 2. All right, so that's what this is telling us to do. That's what this is encoding for. All right, so determinant of everything that remains once you eliminate the row and column containing 2. So basically, it's telling us to get rid of row 1, column 1. That's only going to leave us with a 3. Plus -1 to the third power is -1. The entry in row 1, column 2 is 3. All right. So that's, I'm sorry, row 1, column 2 is 1. Not the wrong thing, obviously. So the determinant of everything that remains, if you eliminate row 1, column 2, there's only one value there, so it must be the number 1. So product 6, product -1, result 5. All right, so that's 3 different ways to get the same value. All right, now we got to do that using a 3x3, but the key is not so much how you get the determinant as much as it is what does it mean. All right, so we know that this, in 3 different ways, we got the area of a parallelogram based off of these computations. All right, so projected out into 3 dimensions, now we're looking at a parallelepiped. All right, so these vectors 1, 0, 1, if we're assuming the same convention here, 1, 0, 1 is one corner vector, 5, 1, 2 is another, and -4, 1, 0 is the last one. All right, those 3 vectors in space form the basis of the parallelepiped that we're looking to form the volume of. So we get down to business. We're looking at 3 separate computations, but it goes a little bit quicker, as you know. We're looking for the determinant of A. So -1 raised to the 1 plus 1. That gives you a result of 1. All right. We know that the leading factor in each term alternates in sign. So it starts off with a positive, goes to negative, goes back to positive, and so on. All right. So we can rely on that and save ourselves a step. All right. A sub 1, 1. I mean, if we're working across the top, which this formula is calling for us to do, would tell us that this entry is going to be a 1. And then the remainder of it is going to be based off of whatever you would get if you eliminated row 1 and column 1, which is going to be 1, 2, -1, 0. All right. So 1 times 1, equality 1, times diagonal down minus diagonal up. Diagonal down gives you a 0. Remember, that's the shortcut, diagonal down minus diagonal up. So 0 minus -2, so 0 plus 2 is 2. So that's my first computation. The second computation, plus, we now know it's just going to be a -1, because again, we know they're going to alternate in signs. My second entry is the number 5. We're eliminating row 1, column 2, row 1 and column 2, I should say. So 0, so I get the 5 in there. So we're looking at 0, 1, -1, 0, which is really nice because that zeroes out. All right, diagonal down, well, on the diagonal down anyway. All right, so diagonal down zeroes out, diagonal up is -1, diagonal down minus diagonal up. So 0 minus -1 is going to be a positive 1. All right, so that's our second computation. Our third computation, and all of this, again, is based off the fact that this formula tells us that we're working across row 1. All right, based off of this notation here. If it said A sub ij, all bets are off. I'm choosing either row 2 or 3 to work with, because then I can incorporate some zeros as coefficients and make my life a little bit easier. But they're not letting us off the hook, whoever they are. All right, so we know we started off with a positive, we went to negative, so we know it's going to go back to a positive. Now we're tackling the entry -4. And the 2 by 2 square matrix containing the rows and columns that do not contain row 1, column 3. All right, so 0, 1, 1, 2 down the lines. All right, so we're looking at 1 times -4. Diagonal down is 0, diagonal up is 1, 0 minus 1 is -1. So we got 2 plus -5 plus 4. Result, be a 1. 6 minus 5 gives you a 1. So looks like we're in pretty good shape there. All right. So that tells me that the volume of this parallel pipe head is going to be equal to 1. All right. That's all based off determining the determinant. Moment of pause where I'm like, okay, I'm about to say that. And here I go. All right. So that's a little bit of a refresher on that. You know, we didn't really dive too much into the meaning behind the determinant. There was always that promise of, well, what if what if we just sit tight and wait until later on in the course? For now, just take my word for it, and everything will be revealed. You know, that was a couple months ago, a month and a half ago. Now we're at the point where I gotta pay that off. All right, so that's my job now. But still in the part where refreshing our memories, because we got to get to the point where we're taking this into the next phase, if you will. You know, you're looking at all this stuff, it starts getting a little juicy. Right, so the determinant's going to help us in that regard. All right, so I alluded to it before, but the cofactor, if we're using the IJ cofactors, things can get a little cleaner, because all we would be doing is establishing that instead of saying that we're working across the first row, we're working across whatever row we want. So in this case, same question, it's just now we're working across the third row. All right, that's a row that incorporates a 0 in it. That's nice. All right, so all we're doing here is we're just verifying that we're going to get the same answer. So the determinant of this, we're going to start off with a -1. This time it's raised to the I plus j power. All right, so again, it's still 1, 2, 3 for the i's, 1, 2, 3 for the j's. So the entry that we're focused on here, let me get this highlighter out of here because it'll be pretty obvious where we're working in a sec. We're in this position. That's the first row, the third row, the first column. So I, -1, sorry, to the 3 plus 1 power, multiplied by the entry in that position, multiplied by the determinant of everything that remains if you remove the row and column that contains that number 1. All right, so that's the 5, 1, -4, -1. All right, so a little bit more complicated, at least for this one, in terms of finding this determinant, right? But it's 2 by 2, so how bad could it be, right? I mean, it could be pretty freaking terrible if you screw it up, which is usually what I do. But these guys over here, the negatives raised to an even power, so that's going to 1, times 1 is still 1. So all that's going to remain for this component is just the determinant of that 2 by 2 square matrix. So -5 minus -4, so -5 plus 4 is going to be a -1. Then plus, slide on over 1, -1 raised to the 3 plus 2 power, or 3 plus 2 power. The entry there is 2. The 2 by 2 square matrix that remains when you remove the third row in the second column would be 1, 0, -4, -1. All right, so we have the -1 from before, plus -1 to an odd power is -1 times 2. Diagonal down is -1, diagonal up is 0, times -1. But then the last entry would be -1 to the 3 plus 3 times 0 times the determinant of a 2 by 2 square matrix when you remove the row and column containing that number 0. However, since one of the factors is 0, the whole thing's going to 0 out and becomes irrelevant. All right. So we're looking at -1 plus those two negatives offset each other. So -1 plus 2 is equal to a +1. So we get our volume with a simpler set, maybe. I mean, depending, right? You could also look at it based off of that theorem below. Good theorem, helpful, but no theorem is truly good if it doesn't give you a basis to understand. That's an overused word of the day. So basis could be the word of the day, or is the word of the day, basis, right? Because really, understanding the concept of a basis is tantamount to success. So now I'm actually officially making the word tantamount a second word of the day. So we have two words of the day: basis, B-A-S-I-S. I might have actually even used that one before. I can't remember now. It's all a blur. And tantamount. All right. So a 2 for 1. All right. Well, no, 2 for 2, because I'm giving you bonus credit for each one. All right. So, yeah. So let's actually use the IJ cofactor expansion in order to be able to handle this one. And we'll work across the third row again. So the determinant of matrix A again, rows and columns. We got 3 rows, 3 columns. We're in the third row of the first column. So we're looking at -1 to the 3 plus 1 times the entry is 0 times the determinant of whatever. Who cares, right? Because it's not going to amount to anything. So 1, 2, 3, 4 things, doesn't matter. All right. Plus, move it over. Same idea. -1 to the 3 plus 2. Still the entry is 0, and still whatever remains is not going to make a difference because we have that 0 in there. It's all going to zap away anyhow. But when we get to the 3, different story. Now, you may wonder why I'm even bothering to write any of this out. Right? In this case, it's actually not going to make much of a difference. But you see, we still have that sign progression. Right? So this one's positive. This one is negative. The next one is going to go back to being positive based off of the alternating signs. But what if the 3 was the middle one? And what if it was in the bottom row, 0, 3, 0 instead of 0, 0, 3? Well, then you'd have a problem because you'd come up with a positive answer when your answer should be negative, most likely. So we got to be careful about that. So what I do is I at least take note of what the sign progression would be. I don't actually write all this out. I'm like, okay, well, it's the third one. So positive, negative. Okay, it's going to be positive. So I'm not going to worry about that. But this is the really rote by hand way of doing it. All right. Oh, so multiplied by 3, multiplied by diagonal down minus diagonal up. Yeah. But it's containing the numbers 1, 19, well, 1, 0, 19, and 2. All right, now this is not going to end up being a proof by any stretch, but it is a justification because we know that the first 2 terms are going to zero out. This one ends up being, if we carry out this time, I'm going to actually do it out. The diagonal down is going to be the 1 times the 2 minus the diagonal up, which is irrelevant because 0 times anything is going to be 0. So what we're going to get here is a product of 3 and 1 times 2, or 3 times 2 times 1, or 1 times 2 times 3, or 2 times 1 times 3. It doesn't matter. But what happens is these numbers are consistent with the entries in the main diagonal. And if you actually carry out this in the form of a proof, and I mean, different people teach linear algebra different ways. By the way, the answer is 6. I mean, hopefully you're not, but it is. Different people teach different linear algebra in different ways. I like to do kind of a nice mix between the theoretical and the proofs, and then the practical along with the technological application and all that good stuff. Some teachers are like, well, if you're not doing proofs from the beginning to the end, then you're not doing it right. And other people are like, well, if you don't show them what it's used for, then you're not doing it right. So it's kind of a battle. I think I found a pretty decent happy medium, or at least one that I'm comfortable with, and my students don't hate my guts at the end of the course, so that might be something. I don't know if that's necessarily always a good thing, but most of the time it is, I think. But I look at this and say, this is cool. You know, regardless of whether you do an actual proof, this is a cool relationship. If you were to, instead of having numerical values in here, instead of the 1, you would have a sub 1, 1. Instead of the 19, you have a sub 1, 2, and the 45, a sub 1, 3, and so on. If you carry out the proof by cofactor expansion, you'll see that the determinant of a triangular matrix, and the way we know a matrix is triangular is you use the diagonal, the main diagonal as a line of demarcation. If it zeros entirely on one side or the other, it's triangular. This one's called upper triangular because, you know, if you tilt your head and look at it, the numbers form a triangular shape, all right? The lower triangular would be the other way, all right? But you would see, if it's a triangular matrix, that these computations would give you a final result of just a sub 1, 1 times a sub 1, I'm sorry, a sub 2, 2. And then the coefficient of that would be a sub 3, 3, product a sub 1, 1, 2, 2, 3, 3, which are the entries in the main diagonal. It's actually really cool. All right. And why? Because I said so? No, because it just is. You know, it's one of those things. You know, when numbers kind of work out nicely into a tangible relationship, whether you're a math person or not, when you discover a relationship like that, even if it's been discovered a billion times over by other people, but you discovered it for the first time yourself, you still feel like $1 million. It's like, wow, I did that. I created that. And this is one of those things, you know. And you can look at number 5, you know, compute the determinant of this. This is a 5 by 5 square matrix. And you're like, geez Louise, are you out of your mind? Yeah, that's what people keep telling me. No, this is something, you know, if you look at the directions, doesn't say anything about using cofactor expansion or anything along those lines. What it says to do is find the determinant. Right? In a linear algebra class, I would absolutely ask my students to figure this out using cofactor expansion. It's actually a pretty easy problem, except you have to get into, you might be familiar with the term transpose, where you take your first row, first column, and make it your first row. Your second column, make it your second row. Your third column, make it your third row. Excel does a pretty good job of that. If you copy a set of data and then you paste special, you paste it as a transpose, it'll take all your columns and organize them as rows, and it looks great, depending on if that's what you want it to look like. Right? What that would do is allow that first column, which has all zeros but one value, to become a row, which would then allow me to use my cofactor expansion across rows. But then, you know, it's more, now we're really getting into linear algebra. The concept of a determinant isn't just specific to traveling across a row. You could use the same idea just working up and down columns. Right? So there's a lot more to it. You can use them in conjunction with one another. In the first go round, you can work down the first column, and then you say, okay, well, now I find it mostly convenient to go across the third row, so let me do that. You know, so there's a whole lot that goes into it. But for us, it's an exercise in typing values in without screwing it up. At least until next semester, where some of you take linear algebra. Which I will not be teaching, definitely during the summer, maybe in the fall. We'll see. So, I mean, I don't know. I don't want to get too far into that, but because I always figured they were gonna, and I've said this for years, so it's kind of like rehearsed at this point. But I figure that there are students that look at the way I teach and say, perfect. That's exactly the way I like to be taught. This teacher does things perfectly the way I would like them to be done, and it fits with my learning style, and it's wonderful. And then there are other people that are like, this guy can't get out of his own way. He keeps going off on like, and everybody else kind of falls somewhere in the middle. So I look at it like, you either love me or you hate me, or you're undecided, in which case you don't really care one way or the other. I'm just another face. I'm just or a name for you to forget 20 years from now. And when somebody's like, hey, did you have any math teachers you didn't hate? And you'd be like, yeah, there was this one back in college. I can't remember his name. I probably fall into that category a lot. But yeah, I have no expectations that people are that think I'm the best at really anything. I try a lot. I try hard. And so if that works for you, then we're good. Why am I talking about this? Because we're selecting courses this weekend for the fall. And I tend to share it as soon as I know it with my current students, in case anybody doesn't hate me enough to want to take me as a teacher another time around. All right. Possible it might not be relevant if I'm teaching like a stat class in Calc 1, it might not matter, but I'll keep you posted if that's something you're interested in. Anyway, I bought myself enough time to type in the data. That's usually why I go off on these tangents. Just I need time to type some stuff in. So determinant A, and you're like, whoa, Nelly, that's a negative number. Well, yeah, it sure is. So it means one of two things, both unfortunately equally likely. It means either I typed it in incorrectly, or it's just negative. Right? So if we want, in a geometric sense, if we want to capture an area or a volume, then we would drop any negatives that we get, because what we're looking at is not only a measure of the absolute value of the area or volume, we're also looking at the direction in which all of this is plotted, the movement from one vector to another. All right. So the placement of your columns will dictate the type of sign that you get. All right. So let's take, for example, well, with 2 by 2 squares, it's kind of tricky because it almost always kind of plays out the right way. Let me see. Yeah, it'll work. I'll just show you real quick. So here we went in a counterclockwise fashion to get from U to V. All right. Starting with vector U, which was 2, 1, going to vector V, which is 1, 3. Had we gone the other way, had we done VU, which would be in the clockwise fashion, that would be 1, 3, 2, 1. Diagonal down would be 1. Diagonal up would be 6. 1 minus 6 would be equal to -5. So this determinant, so 6, 1 minus 6, -5, would give us the same absolute, just with a different sign. All right. So that negative is only suggesting direction, all right, from one vector to another. The issue that we run into in 3 dimensions is the progression from one vector to another. Well, how does that work? Because it's not just a matter of going around a unit circle, for example. All right. So what's happening is you're actually looking at the trio of vectors that are pointing away from you. and you're still following that clockwise or counterclockwise relationship, starting with the 101, then traveling to the 512, and then the negative 410. All right. Following that progression gives you a volume of 1. Change up the progression. It still has to be in sequential order. All right. Because if you skip one along the way and go a different route, then it's possible that you may not even get the corners of a parallelepiped. But let's say you have those 3 in that arrangement. You could start off at the, my index finger here, go to the thumb, and then back to the middle finger. It's still consecutive in what would be a counterclockwise movement. So that would still give you the positive 1. It's when you go in the reverse order, that's where you get the negative 1. Right? So we take the lessons that we learned from that and expand that up into 5 dimensions, where we would say, okay, so there were 5 consecutive legs to this 5-dimensional parallelepiped, but somehow it went in the reverse order of what it ought to have been. Right? So maybe it should have been the last column first, and the second to last would be second, and the third from the, third would be third anyway. Just flipping the first with the last and the second with the second from last. Then that would give you the volume with a positive number. But since we're only looking for the absolute value of this, boom, 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 boom equals boom. That's a volume. All right, but it's a 5th dimensional volume, which we have no context to understand. All right. So it's still going to capture space, but we don't know in what capacity because we can't conceptualize that, right, in our mind's eye. But if you look at it and say, all right, volume in 3 dimensions is based off of those 3 dimensions. That's your 3-dimensional volume. The 4th dimensional quote unquote volume is if you could have a figure in 4 dimensions, if you can perceive that, then whatever space was captured within that figure, that would be the measure determined by that determinant. All right. So that's a little bit of review and a little bit of contextualization of the concept of a determinant, so that we can get into linear transformations. And so the linear transformation is actually just talking about, because we're going to do linear transformations and then other types of variable transformations, right? It's talking about just moving a vector, a point, a figure in space based off of some predetermined rule, right? So I'll just read the blurb. A function f from the set V to the set W, right? So from one space to another is a rule that assigns to each element x in V exactly one element f of x in W, all right? So that's, basically we're talking about, they used to call it the function machine, where you put in your independent variable, you shake it all around, and it spits out a transformation of that x variable, which is now known as f of x, the dependent variable. All right. Transformation or function or mapping T from some real space N to real space M. So basically it's saying dimensions not necessarily the same. All right. It could be real space 2 to real space 2, so 2 dimensions, or it could be a real space 3 to real space 2, in which case you're decomposing it down into 2 dimensions from 3 dimensions. It's a rule that assigns to each vector x in that real space a vector t of x, right? So that's the relation, right, in that subsequent real space. All right. One is the domain, and the other is called the codomain. We tend to stay away from range when we get into multivariables, because if you're dealing with, let's say you have 5 variables, like you're in 5 dimensions, you have 4 unique independent variables and oh, I'm sorry, 5 unique independent variables, then you could be yeah, they could be independent or dependent depending on how you define it. If it's implicitly defined, then it could go either way. But let's just say 5 unique variables. If it's in 5 space, then they, like which one's the output? We don't know. Any of them could be the output. In which case, they're all going to have their domains. But whichever one you define as the most important variable, if you will, those would be the ones, or that would be the one that you would refer to as a domain. Everything else would be a codomain, right? So that's what the notation is getting at, and anything that results in it from a transformation is known as an image, right? So I have the example here, and these are all column vectors, all right? So you have a matrix 1, 1, 4, -3, -1, 2, 2, vector U, vector B, vector C, right? And what this is showing, or at least we're going to show, define a transformation going from real space 2 to real space 3 by the rule T of X equals AX, so that T of X equals AX is based off of this relationship. So, so here is my A. That's my matrix A. And here's my vector X. The result is what you would get if you multiply these two things, right? So this is actually going to be the transformation matrix, or transformation vector in this case, P of X. So this is the transformation vector. All right. So the way we would carry it out is just through matrix multiplication, but that part can be a little tricky if you don't have any experience with that. All you're doing is you're taking each row of the appropriate matrix and multiplying it by the column vector x1, x2. All right. And then it's essentially the case that you're dotting those two vectors together. Right. So what we're looking at here, and let me actually bring this over and just kind of emphasize it for you. All right, so pop that in there, prop it a little bit, because that equal sign out of there. All right, so what we're doing is we're taking each row and multiplying it by the respective column. Well, it wouldn't be respective, just the column vector. All right, so it's going to end up being the dotting of 1, -1, and x1, x2. So when you find the dot product here, you're looking at x1 plus -x2, which gives you this entry. Oh, that's terrible. All right. So you're doing the same thing here. The 4, 2, that row is getting dotted against vector x1, x2. 4 times 1, I'm sorry, 4 times x of 1, 4x of 1. 2 times x of 2 is 2x of 2. And then hopefully you can see the relationship. This, by the same reasoning, is going to give you this. You can't make a rectangle. All right. So that's the rationale from where that came from. I didn't want to, because I know I'm giving you the short version I didn't want to make it too short and be like, oh, and here's a magic rule that just works because it said it does, you know. I want to show you a little justification. In fact, let me just pop that last little thing in there. So -3, 2, dotted against x1, x2, gives you the result of -3x1 plus 2x2. All right. So that's where all that information is leading. And I guess I probably could even, just for consistency, throw in that last one. So 4x1 plus 2x2. All right, the more corners I try to cut, the more I end up showing the extra steps. All right, so that gives you a little bit of a sense, hopefully, that what we're dealing with here is a way of transforming a vector based off of some predetermined matrix. And if we know what that vector x1, x2 is, then that's really it. Then we have a relation, right? That x1, x2, if that's 1, 1, I now have a means by which I could determine the transformed vector. And it's important to realize that this 3x2 matrix that we're multiplying by the x1, x2 is transforming a 2x1 vector, which is really the same as saying a vector in 2 space into a vector that would then be in 3 space, right? So these questions, they came directly from linear algebra. I think I just copy pasted them without even really looking. Let's see, X. Yeah, I mean, some of them are fine. Find TU, the image of U under the transformation. Yeah, I mean, A is fine. All right, so U is the coordinates 1, 2, or vector 1, 2, I should say. All right, so we're transforming this based off of that rule. All right, so we would then, we would do one of two things. We would actually multiply the 1, 2 using matrix multiplication by matrix A, or we can take advantage of our handy dandy new rule here. Because this is the model that would allow us to determine the transformed vector dependent on what the first and second entry is of the given vector. So if I let, turn that on. If I let U and X be the same thing, if I let X equal U, then I can replace X1 with a 1, X2 with a 2, and then just carry out the substitutions. All right, so I'd be looking at 1 minus 1 times 2, 4 times 1 plus 2 times 2, -3 times 1 plus 2 times 2. So 1 minus 2 is -1, 4 plus 4 is 8, and -3 plus 4 is 1. So that allows us to take something that's 2-dimensional and bring it up into 3 dimensions. The issue is we haven't really talked about what purpose that would serve, number one. And number two, we haven't talked about going back the other way so that we could take something that's in 3 dimensions and look at it as if it were in a 2-dimensional plane and what that would mean. So that's something else. I don't think there are any other questions in this set here that are specific to what we would be using. So I'm just going to toss those other ones Find an X in R2 with image under T is B. Yeah, that requires solving a matrix equation, so we'll stay away from that. More than one. Yeah, that's what homogeneous solutions and the determinant of the range. Yeah, that's different. Okay, so it's really just A. So there's a typo for somebody. Eliminate B, C, and D on page 86. So that's the intro to linear transformations. What we're going to do, starting next class, is talk about changing variables. All right. So we start off with the planar transformations. So that's the case where we get some relationship that allows us to transform essentially the basis of the rectangular coordinate system. Instead of going from 0 to 1 along the x-axis, each tick mark is 0 to whatever we want, but also to redefine functions in terms of other systems, coordinate systems, right? Coordinate systems of our choosing based on a rule, not necessarily related to rectangular, polar, and things like that. All right. And then once we've covered that, then we could actually get into using matrices as a shortcut technique to help us perform these transformations. And then once we do that, we'll bring the determinants back in so we can put it all together and talk about volumes and areas for the transformed figures as opposed to the pre-transformed figures. All right. So the rest of the week is pretty much going to be along those lines. That's the new stuff that I tacked on, which is going to tie in nicely with something called Jacobian determinants, which is where we bring the partial derivatives back into play and we start getting into surface area and stuff like that. All right, so pretty heavy stuff, but we take it a piece at a time so that we don't go too crazy with this. But that's where I'm going to leave it for this evening. Stop the recording.